Okay, so we're back for multivariate models, and we're going to be talking about ordination, and our first lecture is going to be on distance matrices. And no required readings for class, but a nice paper if you want to dive more deeply into thinking about how to actually transform your data. When we get to that, it can be challenging to decide what to do, and here's a paper that might help you. And so as a reminder, we're thinking about multivariate analyses, and there are several ways to look at multivariate patterns from a matrix of Y variables. And today we're going to be talking about ordinations, which includes PCA, NMDS, and these are ways to visualize your patterns in your data. So you want to use ordination techniques when you have a matrix of Y data, and you want to explore the multidimensional aspects of that Y matrix. And so this type of data exploration is common in community ecology, where you have simultaneous response of multiple members within a community. So you could have the composition of plants within quadrats or of your community, composition of aquatic organisms within a water sample, composition of microbes in a leaf or soil sample using genetic data. Another big field that uses this type of ordination is morphometrics. And so in this field, you are examining complex shapes of a sample, so your skull shape, your limb shape, bone structure, etc. So you're looking at shapes of things. And then it's also common in chemical or molecular makeup studies. So if you want to look at the composition of metabolites within a tissue sample, or a soil sample, or a composition of proteins in a sample, anything where you have multiple Ys that are making up a community of ones in one sample, this is a great technique for. And so I want to really emphasize that all of this ordination we're going to be talking about is pattern description, and that's we're trying to describe now the whole pattern of the data, not just a piece of the data. And so it's like the classic elephant example. If you have a bunch of people blindfolded trying to examine a small part of the elephant of your data, you might get a different idea of what it is if you look at the data all together. And so that's why ordination and using all of your Y data can be really useful. And so thinking about it a little more concretely, like what we're going to be doing is we're going to be trying to understand the data in a multi-dimensional space. And we're going to start by describing the distance between all these data points using a distance matrix. And so that's what this lecture is about. How can we describe all of those points with a distance matrix? Okay, so the basic process for which you work through ordination and Permanova techniques, which we're going to talk about in a little bit, is that you start with your data. So you go and you sample soil, say, and you look at all the microbes within a soil sample. So you're looking at the communities of your soil microbes. You take that data, you create a distance matrix, which is what we're going to be talking about in this lecture, and then you transfer that into either visualization through ordination or analysis through Permanova, which is this last image. And we're going to get to that in a different lecture. So just to remind you what your general data structure should look like, you're going to want to have your data set up so you have your individual samples or your observations as rows, and your species or metabolites or chemicals or whatever your unit is as columns. So say you're thinking about plant species within a quadrat, you would have your quadrats as site 1, 2, 3, 4, and then you would have species 1, species 2, species 3, species 4, etc., all the way across as your columns. And so that's what we're looking for in our data. So to be able to translate this type of data into any sort of analysis, we need to figure out a way to relate each observation, which is a row that's made up of different elements or species or metabolites, etc. We need to figure out how to relate them to each other. So we need to use distance matrices. So when thinking about the properties of a distance matrix or your distance measures, they have 4 properties. So first, the minimum distance is 0, and that occurs when 2 observations have exactly the same composition. Or in other words, when yij equals yik, so y is your row, your observation of a bunch of different y variables, and I is the species composition, so each species, and k and j is the site. So when the composition of 2 of your sites are exactly the same, then your distance is 0. If your yij does not equal your yik, so if 2 of your sites do not have equal composition, then your distance between those 2 sites, which is djk, the distance between plots j and k, sites j and k, that's going to be greater than 0. And the third property is that the distance between 2 sites is always symmetric. So your distance from site I to j is always the same as j to I. And then the fourth property is not met for all metrics. We'll get to that in a second, but it's the triangle inequality. And so if you have 3 sites, say I, j, and k, then the sum of any 2 of your distances between those sites is going to be greater than or equal to the third. And so you can see in this image on the left, you can see that if you sum any of those 2, they're equal to be greater than the third distance. So d between those set of 3 sites. So dik and dij, when you sum those are greater than djk and all the way around. However, you can have a set of 3 sites where that's not necessarily true. So if you look at the image on the right, you can see that dik and djk, if you summed those, they would not be greater than dij. And so metric measures satisfy all 4 of these criteria, and semi-metric measures, such as Ray-Curtis, which we'll talk about in a second, violates number 4. So some can violate that 4th triangle inequality property. Okay, so let's talk about some common types of distance measures. So I found these really great illustrations online using Kung Fu Panda cartoons, which I've never seen, but now I really want to watch, of these nice illustrations of these different distance measures. And so I thought I'd throw them in there to help illustrate, and we can thank dataaspirant.com. So, okay, Euclidean distance, which is as the crow flies. So this is just the straight line distance between 2 points in space. And that can be solved using this equation, but that actually should be yij minus yik. I apologize that L got in there. I will change it for the lecture, for the PDF. And so here, just to remind you that djk is the distance between samples j and k, so between the panda and the leopard, I think. Excuse me, between the tiger and the leopard, between samples j and k, and where yij equals the abundance of species I in sample j. So then there's also Manhattan distance, and that is often called the city block distance. And so you can think of your 2 points in space, sites points j and k, and it's always up and over. So instead of drawing that hypotenuse between the 2 points, like for Euclidean distance, here you're going to go, you're going to think about your rise and your run, so up and over. And so here djk is equal to the sum of the absolute value of yij minus yik. And again, djk is the distance between samples j and k, where yij equals the abundance of species I in sample j. Okay, so now moving on to some that are a little bit different. So we have the Jacquard distance, which is based on presence-absence, and this really emphasizes rare species, if that's of interest to you. And here the equation is djk equals a plus b over a plus b plus c. And here, again, the distance is the same, but a is the number of species only found in sample j, B is the number of species only found in sample K, and C is the number of species in both. So here you can say set A and B were really sites J and K. All of them, you have either the zeros are not pictured here, right, of course, but you have your ones, so you have your species that are at site J and species that are at site K. And so in A you have 4 species, and B you have 5. But in A you only have 2 species that are not in B, and in J in B. And so in B you have 2 species that are, let's see, you have 3 species that are not in A. And so that's how you solve that. But again, everything is 1 or 0, so all species are equivalent here. And that's in comparison to Bray-Curtis distance, which emphasizes rare species but uses abundance instead of presence-absence. And so again, here's your formula here at the top. And so again, thinking of set A and B as sites J and K, here you can see that, yes, there are 4 species in site A and 5 species in set B, but the panda in set A is much bigger than the panda in set B, so there's a lot more panda in set A, and so you can sort of see the differences there, right? There's a larger monkey in set A, monkey with a stick in set A, than monkey with a stick in set B. So that's kind of what you're thinking about when it comes to Bray-Curtis. You're thinking about abundances. And then finally, one that I wanted to mention was the Canberra distance, which is often used in metabolomics. It's quite similar to the Bray-Curtis, except for you're going to be multiplying your equation times 1 over the number of non-zero entries. And so one thing that we need to think about when we have this data is transformation. And so we have our abundance data of multiple Y variables, for example, species, metabolites, molecules, etc., per sample. But before we compute most types of distances, we need to standardize the data. So we need, there's multiple ways to think about standardizing your data, but say you, one way is to convert the abundance to some function of the abundance. So for example, you can convert to presence absence. So if you're using Jacquard distance, then you're going to want to convert to presence absence. A lot of times you'll want to use log if your values are really all over the place. Metabolomics commonly uses that. You can also use your abundance to the 1/4 power. I don't see this quite as much, but it can be used when you have extremely skewed data and it's patchy and you have a lot of zeros. So some examples are aquatic invertebrates, but again, use this with caution. If your field is accepting of it, then I would say that's a good one to use. You can also convert to site proportion or divide by the site totals. And so this is really common with the Bray-Curtis measure. So if you're going to use Bray-Curtis, you want to divide by site total often. You can also standardize by species maximum, and that equalizes contribution from rare and abundant species. And then the classic Wisconsin school that does a lot of vegetation analysis uses the Wisconsin double standardization, which is standardized first by site total and then by site max. So the trick is, how do you decide on a transformation? Probably the most important thing to do is think about what your field does. So if you see in a lot of papers that are doing similar analyses with similar data, if they're using certain transformations or certain distances, I would recommend using those. But if you aren't sure, there's some things you can think about when considering your transformations. And so a lot of it comes down to how much do rare elements count versus abundant ones. So how much do you care about rare species or metabolites, etc.? So if you do care about them, you could consider presence absence, right? Because that really weights rare species more equally to abundant ones. You could also divide by site totals or choose a measure with absolute values. And does your total abundance matter is something else you could think about. So if so, then you could use your site max, but if not, divide by your site totals, as in with Bray-Curtis distance. So we're going to run through a toy example so you can see what this looks like. So I just made a simple data matrix called toy here. And so you can see we have 4 observations or 4 samples and 5 species A through E. And then there's different numbers of all of them in each sample at each site. Okay, so when you want to do your standardization, you use the function decostand in the vegan library. And you can click on the link there to see more options for how to standardize. I've only used a few here that we talked about because you get the idea and you can go to that website to look. But you can see here I've standardized the toy data set in 3 different ways. Standardized it by the total. I've used a log transformation and also that Wisconsin double transformation. And so you can see you got quite different results out. Okay, and so the next step is to calculate a distance matrix for everything. And remember again, along the diagonal, it's going to be 1 because, or excuse me, 0 because any site with itself, the distance between any site with itself is going to be 0 because they're exactly the same. And so here, I'm going to show you some examples of different distance matrices. So you use the vegdist function again in the vegan library for this. And again, please check out that link for more options because there are a lot of ways to specify your distance matrix as we've talked about. So go ahead and dive in and examine that if you want. Check out some other options. But here I'll run through the ones that we talked about in the lecture. So you can see Euclidean, again, straight line distance did not actually, for this case, it did not actually transform it because sometimes when you're thinking about points in space, for example, you don't necessarily want to transform it or standardize it by a site total because that wouldn't make any sense. You actually care about the distance between each site because they're actually physical locations sometimes. So here I didn't transform it. And then the Manhattan distance, which is that city block distance, you can see that's slightly different than Euclidean, which relies on the hypotenuse. And then Canberra distance. And so I just did not transform that, but just wanted to show you that. Probably should have log transformed it though, which is fairly common in metabolomics. And then just a few more because I wanted to run through them all. So first is Jacquard. So here you can see that this one had to get standardized by presence absence, which is why it's toy P. And you can see the code under the hood if you want to see how I did that. And so then I made the distance matrix using Jacquard, and you can see how different that looks when you use something that doesn't weight rare species quite as much, such as Bray-Curtis. And so the last 2 are Bray-Curtis distance matrices with and without a species total standardization. And so I know this is a lot. There's a lot to think about as to which distance matrices you want to use if you have community data. But again, I would really strongly recommend looking at the literature to see what your field does because that's going to be the easiest way to justify your work. And so with that, please complete quiz 9.1 on Canvas and continue on to the next lecture.